So welcome everyone to this 12th session of Statistical Learning in Practice. And as I was just saying, we'll begin with classification today. And this is the second main block of the course before we end it with time series. Right. So classification. Okay. So classification, we will discuss this in a bit, but it is a special case of regression. And the idea is that rather than having, assigning a certain real value to the covariates, what we're going to assign is a category, a class, okay? So this is a very, very important task, right, in modern applications. So you could be thinking, for instance, of image recognition. So when when you have a self-driving car, then what it is doing is just all the time, sort of constantly in time, it is trying to identify what are the objects that are moving, in front of it, and therefore, it is trying to put into categories all of the data that it sees. And what we're going to focus on in this course is what is called supervised classification. Okay, so supervised. So what does this mean? Well, it means that the data that we're going to feed the algorithm with, so the training data, is going to be labeled. And by that, I just mean that we will, the data will come just exactly as in regression. So we'll have an X and a Y. The X will be the covariates, and the Y's in this case will be the labels. Okay, so there is another type of classification problem, which is not really part of regression, but which is called unsupervised classification. And in this one, you don't really get the labels, and rather you know that there are certain categories. And the problem is really trying to classify these different covariates into the different possible categories, but without really having told the algorithm, where the training data is sitting in, regarding the classes or categories. Okay, so just to fix notation, so then the data then is given by this pair again, XY, and in this case we're going to say that this is contained, this belongs to this calligraphic X times a calligraphic L now. So the calligraphic X is just the sample space as usual. Here, sample space. Okay, which we're going to assume to be this, generally. Okay, and then the this calligraphic L is what is called the set of labels or set of classes. So that's where the L is coming from, and without loss of generality, what we're going to have. So L is going to be 1 to capital L for some L in the natural numbers without loss of generality. Okay, so because we could be saying that the different labels are a car, a dog, a cat, and so on, and but we can still assign numerical values to them, right? And so if we say that we have capital L labels, then our calligraphic L, we can simply write it without a lot of generality by this, in this form. So 1 to capital L. Okay. So what are the assumptions? Well, in this problem in general, So I think it should be clear, right, that what we are really assuming is that the label given our covariates is going to be a categorical random variable, okay? With these probabilities, actually, so maybe I'm missing first parameter, even though it's sort of clear from the P sub capital L. But we have capital L categories, and therefore these, the probabilities of each of them happening is described by a probability, which would be this P. So what we are, so the PL then is just the probability of Y being L given X, okay? Which is of course, greater than or equal to 0. And then the other assumption, but this is really just coming from just writing that Y given X is categorical, is simply that the sum of the PLs is 1, okay? Okay, so maybe we can say so here. Yeah? Okay, so now let me define a classifier. So a classifier, maybe let's be a bit more. Okay, classifier is a Borel measurable, and again, we don't really care about measurability in this course. Borel measurable. So Borel measurable function psi that is going to go from the sample space to the set of labels, where with the interpretation that this psi x is the class assigned to X in this chigraphic X. Okay, so I think the setting should be clear. And as I said before, let me just remark that classification is really a subset, of regression. Okay, and now, given this observation, we have an implication of it. Okay, so this means that we're interested in modeling this guy. Okay, although this really should be a question at the moment. Yeah, are we really interested in modeling this? Because that would be what would pop out of this, of this interpretation of classification as regression, right? So before answering this question, let me just simply say that, you could be thinking, well, if classification is a special case of regression, then why not to put it under the same umbrella, right? And indeed you could, but classification is already, is a very important branch of statistics and machine learning in itself. And so, that start with that answers, this, why we are keeping it separate. But also what we're going to see is that there are algorithms that are designed specifically for classification. So with this, interpretation that we have certain categories, and then the other thing, of course, is that we get certain particularities that are coming, that arise in classification specifically. Okay, so then it makes sense to just set it set it apart and treat it separately. Okay, so to answer this question of whether we are interested in modeling this expectation, we should take another detour as we did at the beginning of regression. Okay, and Okay, so let's begin then with the case of L equal 2, so in which we have two classes. So this is clear, right? So this is clear for L equal 2, since without loss of generality, we have that rather than taking the calligraphic L to be 1, 2, we can take it to be 0, 1. Okay, so it doesn't matter whether we call one of the classes 1 and 2 or 0 and 1, especially when we have two possible classes, right? Okay, so what this means essentially, so this is clear, since without loss of generality, we get this, and therefore the expectation of y given x, right? So now note that the y is taking the values 1 or 0, then the expectation is simply the probability of y being equal to 1, right? Given x. And this is a very sensible quantity to be modeling, right? Because if you think of, this totally determines, right? So this is 1 minus probability of being 0. So therefore, either of the two probabilities totally determines the other one, and indeed the data generating mechanism, right? Because the data generating mechanism is this categorical distribution. Okay, so it's clear then for two classes. By the way, the two classes are basically binomial regression. So we're in familiar waters in some sense. So rather than being strictly speaking binomial regression, what we have here is these Bernoulli experiments. Okay. Okay. Now, what about for more than two classes? Because let me show you that there is a bit of a little complication. So for L greater than 2, modeling this expectation may not be as reasonable. Okay. Okay. And this, I think, should be clear, because if y is taking the values 1 to capital L, then with the expectation we lose a lot of information, right? Plus, what is also important is that we've arbitrarily decided that the y is going to take values in 1, 2, 3 up to capital L. So really this expectation is going to be averaging those values. And if these values have the interpretation of being, different animals, so again, cat, dog, and so on, then what is the interpretation of averaging these natural numbers that we've assigned to each of the classes? It's just not reasonable in that case to be modeling this guy. However, modeling the probability of y being equal to L it's still sort of sensible, right? I mean, this is really something that we would wish to do, because again, this will totally determine the data generating mechanism, right? So how do we, if this is, if classification is a special case of regression, then how do we conciliate these two things, right? Or reconciliate now. So we can reconciliate the two views, or the two, ideas, right? Okay. So how do we do this? Well, we're going to change the set of labels. Okay, so we're going to change the way in which we view the labels. So take calligraphic L to be, to be essentially the set of all of the vectors of length capital L that have as the values, or as the coordinates, the values 0 and 1 only. Okay, so with this choice, we're also going to take y given x to be a vector, of course, right, of zeros and ones and of length capital L. And now the key is that this is going to be viewed as following a multinomial distribution, okay, with parameters 1, P1 to PL, capital L, where the PL now is going to be the probability of YL, so the L coordinate being 1 rather than 0. So we have the two options, right? This is for all L in 1 to capital L. So let me pause here for a sec. So what have we done here? Well, we've said, rather than y taking values in the possible categories, let me write it as a vector of length of the number of categories and set a 1 set a 1 in the coordinate that corresponds to the category that we are assigning to it, and 0 in the rest of coordinates. Okay, so this is an equivalent way of viewing the labels. And what else did I want to say? Well, it sort of comes from this interpretation. So remember, without loss of generality, we changed the label space in the binary classification problem to be this rather than 1 to 2. And so this is what is sort of lurking in the background in this other view. Okay, so what we've said is that for each of the categories we can assign 0 or 1 depending on whether that's the active one or not. Okay. All right, and so now with this view, what we have, of course, is that we can take the expectation. So the expectation of y, so now it's an expectation of a vector. So it's just the it's the vector of the expectations of the coordinates. Then this is now a sensible quantity to be modeling, right? So this is exactly what we wanted to model. Okay, so this is sensible. Okay, so let me then say that we're going to use both. I guess we could call them both views interchangeably. Okay. Okay, so we may take the labels to be following a categorical or a multinomial distribution, sort of without mentioning this. Although generally we'll use the first view, but we'll see, especially in binomial regression, I think maybe actually just in binomial regression, we'll be viewing we'll be viewing the labels in the second way. Okay. So in either case, what we have, so for either, we model eta x L, okay, which is the probability of y being equal to L given x, or the probability of the Lth coordinate of the label vector being 1. Okay, And this is called, by the way, the regressors. Okay, so sort of going back to the terminology of regression. So these are the regressors. Okay. So equivalently, in regression, we may be interested in modeling, slightly different quantities. Okay. So equivalently, we can model, or we may wish to model so the conditional. So remember, I mean, these regressors are, conditional probability mass function, but instead we can, we may want to model the conditional density of these covariates given the value of the label, which we denote by this FL, together with the marginal distribution, or PMF of Y, which we denote by pi L. Okay. Okay. So why is this? Why is it that this is equivalent? So let's look at decision theory again. Okay, and so the following discussion, I will, so it's slightly lengthier in the PDF notes, and it's all, I think, interesting in itself, but, the key bit is what I'm going to mention now, and is that, let these two guys follow this joint density. So and I'm saying density here in the terminology or vocabulary of measure theory. So of course, if the labels, the labels are a discrete random variable, so we wouldn't have a density with respect to Lebesgue, but rather with respect to the counting measure, for instance. And that's what I mean by density. So this joint density is probably with respect to Lebesgue times counting measure. Yeah, but anyway, it's just a density. Yeah. So for some density on this calligraphic X times the set of labels, then, and let me take now the first view. So when, so let me then take the view in which we have that Y given X is categorical with parameters capital L, P1 to P capital L. The risk or test error of a classifier is given by this quantity, capital R, of psi, being equal to the integral over this product space. And then we have an indicator for when the label that we assigned to this X is distinct from a given L, and we integrate this with respect to the density. Okay, And so note that I'm really being a bit sloppy here. So we wouldn't, this would sort of mean that we have the Lebesgue measure as the dominating measure for this bit, but it's, I think you can trust me that it's fine to, well, I think you can accept it as some reasonable notation, as long as you're aware of what's going on. So let me now write this, therefore, because this is not really Lebesgue, but rather, counting measure, then what we have here is the view that, we can use, Tonelli's theorem and write this simply, as an iterated couple of integrals, and write, therefore, this. Okay. This is really, the first expression is a bit sloppy, while the second is the right one. Yeah. Okay. Okay, so this is the test error. Now, what do I want to say? Well, I want you to check something at home. So check following R is minimized. So it's minimized by this classifier, which is, so now, of course, by the way, with calligraphic L, I'm now referring to this set of numerical values from 1 to capital L, because we took the categorical view of the labels. And this guy is going to be the minimizer of the test error. Okay, and this is, of course, for any x in the calligraphic X. Okay, and then the second thing you should check is that this is pi base. Okay, so pi base, for pi given by the pi that I defined above, yeah? So the marginal PMF of y. Okay, so all you need to do is to write this joint density as with respect to the marginal of x given y and the marginal of y, so just use Bayes' theorem, and that will help you, well, as in, if you answer the first part of the question, then the answer to the second will follow from that. Yeah. So just checking that the first part of the question is shouldn't be too hard. Okay, if you think about this last expression here. Okay. So this means that, given that we now write the classifier in terms of this joint density, so it means that we can model F directly and obtain this guy. But generally, F is hard to interpret, okay? Okay, so it's not very simple, generally speaking, for humans to be able to elicit joint distributions. Okay, so it's much easier to elicit conditional distributions together with marginal distributions. Okay, so this is exactly what we can do. So instead, write this fxl as the product of this marginal distribution, of the conditional times the marginal, or the other way around as well, right? So using the regressor and then the so the marginal. Of this X. So what we have therefore following from this is that the pi base estimator is therefore also, any of the maximizers in terms of the labels of the regressor and also of the product of these two guys. Yeah. Okay, so in some sense, what we've, the first bit of this says that we've recovered what we were expecting, right? What we started with, which is that we will, we want to model the regressors, although note that I haven't really used the quadratic risk here, at least not explicitly. So rather, we've used this classification risk, okay? But precisely so the notes have a slightly lengthier discussion because there is a way to view this classification risk as the quadratic risk, okay, in classification, given the second view of the labels, okay, that I introduced above. Anyway, so then we get that modeling the regressor is sensible, but also we get that precisely we can also model the product of these two guys as we claimed, okay, equivalently. So we did this here in this paragraph. So we claimed that it was equivalent to model these two separately to modeling the regressors, okay? And let me just say also that if we so by Bayes' theorem, what we have is the regressor is given by, this product which means that, so modeling FL pi models eta x implicitly. Yeah. Again, eta x will determine the data generating mechanism, so at least when conditional on the x, and therefore this should be the case. Yeah, what we now got. Okay, and then let me also sort of give an additional bit of terminology. So we say that so since given x in the sample space, we choose L maximizing FL pi or eta x. These are called discriminant functions. Okay, so in different words, a discriminant function is a function that a function of the data and the labels that allows us to discriminate between the potential labels given an x. Okay, and so of course these two guys are discriminant functions. Okay, so the rest of the chapter, and I'm still going to introduce some an algorithm actually, but let me just say what the rest of the chapter is about. So the rest of the chapter basically is about different algorithms, which are basically some of the most popular classification algorithms. And what we are going to be doing is to introduce them in an order in which they will be less and less interpretable. Okay, so we are sort of conceptually what we're doing in this course is saying, well, okay, so we have these simple models, let's complicate them because they have limitations, and the simple models have good interpretability, so let me then begin classification with the most interpretable ones, and then build up to more type of black box type of algorithms, which for them there is hardly any interpretability, and instead, what we're going to be wanting to do with them is more prediction purposes. Yeah, so we will be looking for having a good prediction error. So this also sort of joins with the ideas of this. I think it was second section of the first chapter, in which we were sort of comparing, for instance, AIC with BIC as to whether one was a better selection method for recovering the true model, so in some sense with some more interpretability, or really just for prediction purposes. Okay, and let me say that precisely finding or having interpretability for these more black box type of algorithms, so especially I'm talking about deep learning or deep neural networks, is a very hot topic, precisely because they work very well in prediction for prediction purposes. But because they don't have this interpretability, then they are not very suitable for very sensitive applications, like it could be medical applications, or the self-driving cars that I was talking about before. Okay. So let me then begin with an algorithm. So this is now 2.1. So before I introduce the first algorithm, let me say what a linear classifier is, because I'm going to broadly classify classifiers into linear and nonlinear. Okay, so linear classifiers, and as you can imagine, linear classifiers are a lot easier to interpret. Yeah. So this is in some sense, related to GLMs, not the whole thing, of course, but we'll see that we have binomial regression as one of the linear classifiers. Okay. All right. So note something. So given a classifier psi, its pre-images, okay, by which I just mean that we take the pre-image of the potential labels, and here we are using the first interpretation of the labels. So these partition the sample space. Okay. Okay. So this partition the sample space. Okay. So then let me write a definition. So definition 11, which contains 2 bits. So the boundaries of the pre-images of a classifier psi are called, maybe the comma is not necessary, are called the or its decision or classification boundaries. Okay, so a classifier, so this is the second part of the definition. So a classifier is linear if its classification boundaries are piecewise affine. and nonlinear otherwise. Okay. All right, so we're ready now to talk about the first classification algorithm. This is 211, and this is linear discriminant analysis. So it's not really the name of the classifier, but rather the name of the sort of analysis that takes us to the this first classifier. Okay, so this type of analysis was done by Fisher. So we'll see this in the practical, an example that he was using. Okay, so what is the assumption here in linear discriminant analysis? Well, we're going to make a very intuitive assumption that actually uses the second set of quantities that we can put conditions on, or that we can model. Okay, so rather than the regressor, we're going to be modeling this marginal density together with the marginal conditional. Oh my God. So excuse me. We're going to be modeling the conditional density of x given y, and we're going to be modeling the marginal of the labels. Okay. Okay, so assumption is that precisely this conditional, right? So what this is saying is, if we look at the covariates giving rise to the labels, or to the label L, then these guys are going to be normally distributed according to some mean parameter mu L. So this will depend on the class, and then of course belonging to RP, because we are assuming that the sample space is RP. And then the other key assumption is that the covariate matrix is common to all of the classes. Okay, so you should imagine that you have different sort of clusters of data, which could be sort of one over the other perfectly well. When you get a training set. So sort of with some intersection, but these are sort of normally distributed with similar shape in the distribution. Okay, just placed at different points. Okay, in the space, because these are the means. Okay, so then given pi, we have that. Just by what we were saying before, the base classifier is going to be any of the maximizers, and this again is going from 1 to capital L of this in here, right? For pi to be defined. Okay, so this is given some pi. Okay, so we'll talk about this in a sec. Okay, so I want you to check something as well at home. It's the following. So these are, this should be simple calculations. Yeah, everything that I leave for checking. So that what I want you to check is that the classifier can also be written in the following way. So as the maximizer of the following discriminant function. Okay, so the discriminant function is given by -1/2 x minus mu L transpose sigma to the -1 x minus mu L plus the logarithm of this guy. Okay, so this should be clear from taking logarithms and so on. Yeah.
Is the symbol a delta?
Sorry, can you ask again, please?
Is the symbol a delta? Or is it an F? I'm like, just
subscript L.
So what subscript L?
So this bit.
Yeah, but what's before the subscript?
Delta subscript L. Yeah. Yeah, sorry, I don't know how you write delta, but this is the way I do. Yeah, I mean, if you're comparing it to F, then see that I close, that I write it a bit differently. Okay. So, okay, and so this is the first thing to check, and then the second thing to check is that the boundaries, the classification boundaries, of course, or the decision boundaries are given by this set. So it's the set of x's in the sample space such that the logarithm of the regressor for k and regressor for L equals 0, okay? For some k distinct from L. And then the last bit of the exercise is where the logarithm that I wrote above equals alpha. So it can be written as a constant depending on the label, on the labels that we're considering, times x given plus x times some parameter. Actually, if I want to be consistent with the notation, then maybe I should write KL. And this is for some alpha KL, the reals, and beta KL in RP. So let me say that you should also find the values of these two guys. Yeah. I mean, you will do just simply by trying to write it as that. And, as a tip, I guess, this is in terms of the means for classes, the covariance, and the values of that we given this prior. Okay, so then let me end by giving before that. So I was going to say that this is not really a classifier in that we haven't used data. Okay, so generally a classifier is a measurable function of the data, right? So we need to introduce some data. But even before saying that, what I guess I want to emphasize is that if this were a classifier, if it were depending on the data, then this expression would therefore give us that the classifier would be linear, right? Because this is exactly an affine function. Yeah. And this is just and it plays a role, of course, in the decision boundaries. Okay. Okay, so let's now just define this classifier in terms of the data. So definition 12. Okay, the LDA classifier is this LDA, which is the argmin, argmax of delta L LDA. So now this is slightly different. How is it different? Well, it is different in that, so maybe I should have, so let me, just so that it doesn't become too dirty, let me define it below. And so this guy is going to be given by, it's very similar to the previous guy, but we need to introduce the data. And so how do we do that? Well, we need some estimates of the means. Then we also need an estimate of the covariance. And we also need an estimate of the marginal. No, that shouldn't be a K, that should be an L. Okay. What are these estimates? So where, let's go in order of difficulty. So this guy is going to be NL given N, where NL is the sum of, if we look at all of the data points, and I haven't really introduced the data points, but this is exactly the same as before, yeah? So let me say, okay, so let x1, y1, xn, yn be the data. Okay. Then we have that this NL is just the sum of it's the number of data points that had label L. Then the other thing that we can define is the means, which are called the class centroids. Okay, and these are going to be, of course, the mean of those x's whose label is L. So this is the Lth class centroid. And then last, we have the sample covariance matrix that we're going to rescale by this n minus capital L for unbiasedness, and is going to be given by, so now let me write this maybe differently. So let me just write that, say that we're summing over those data points whose label is L. And of course, we look at the sample covariance for each of them, for each of the possible labels. But then because we assume that they're all sharing this covariance matrix, then we can average over them and get a better estimate, okay? And just, let me just remark, or maybe, yeah, let me say remark. That pi hat L is consistent, and that mu hat L and this guy are MLEs. Okay, of course, for the respective quantities. So then they're not only consistent, but there is some asymptotic normality results as well. And this is up to rescaling in the second case. Okay, and then the other, so maybe the second part of the remark is that this classifier is linear. Okay, and this should be, this should be very clear from the calculations that we did before the definition. Okay, so it's exactly the same thing. You will see that rather than getting this alpha KL and beta KL, you get estimated versions of them. Okay, but the decision boundaries are the same. So I introduced them in this data-less case setting so that it was easier to analyze. Okay, so this is the end of the session.